God, we have done it. Limitless clean energy for everyone. Well, not really. At least not yet exactly. We are still a decade or potentially more away from having that sweet unlimited energy to help fuel our addiction to convenience. But we are one step closer as of today. Energy Secretary Jennifer Granholm announced a major scientific breakthrough Tuesday in the decades-long quest to harness fusion, the energy that powers the sun and stars. Researchers at the Lawrence Livermore National Laboratory in California for the first time produced more energy in a fusion reaction than was used to ignite it, something called net energy gain, the Energy Department said. The achievement will pave the way for advancements in national defense and the future of clean power, Granholm and other officials said. This is a landmark achievement for the researchers and staff at the National Ignition Facility who have dedicated their careers to seeing fusion ignition become a reality. And this milestone will undoubtedly spark even more discovery, Granholm said at a news conference in Washington. The fusion breakthrough will go down in the history books, she said. White House Science Advisor Arati Prabhakar, appearing with Granholm, called the fusion ignition a tremendous example of what perseverance really can achieve and an engineering marvel beyond belief. Proponents of fusion hope that it could one day produce nearly limitless carbon.
Many people, when they think of nuclear energy, they think of nuclear fission, which was the energy source in the two bombs used in the Second World War. Very quickly after that, we magnified the energy of those bombs by creating a whole other kind of bomb, which came to be known as hydrogen bombs. The hydrogen bombs don't have the radioactive baggage that fission bombs do. Hydrogen bombs are fusion. So fission, let's back up. Fission, you take a big atom, break it, and you weigh those two atoms, and they weigh less than what you started with. Where did the mass go? E equals mc squared, the mass went to energy. You can do the same thing, but coming from the other direction. You take a very light atom, hydrogen, fuse it together with another hydrogen atom, and you get helium. And your product has less mass than you started with. Once again, you get energy, but you don't have all of the byproducts. We've made fusion for 60 years. The problem was we don't have controlled fusion. And when we don't have controlled fusion, it's called a bomb. But when you control it, then you can throttle it, you can valve it, you can put it where you need to and how you want to use it.
But researchers said it was a significant step nonetheless. It's almost like it's a starting gun going off, said Professor Dennis White, director of the Plasma Science and Fusion Center at the Massachusetts Institute of Technology and a leader in fusion research. We should be pushing towards making fusion energy systems available to tackle climate change and energy security. Nuclear fusion is a process in which atomic nuclei combine to form a heavier nucleus, releasing a large amount of energy in the process. This is the same process that powers the sun and other stars. Fusion has the potential to provide a nearly limitless source of energy, as it produces more energy than it consumes, and the fuel for fusion reactions, primarily hydrogen, is abundant on Earth.
So one of the great problems is the containment of such very high temperature gas. And because the gas is like ionized, which means there are free electrons moving around, you can contain it in a magnetic vessel, a magnetic bottle, a magnetic shape, so that it tries to escape it, but it can't because it's charged and it repels the magnetic field. These are the challenges that the physicists faced for decades. So now it's up to the engineers.
Okay.
Once we get the physics figured out, which it seems like we have, then the engineers say, can I make that smaller? Can I make it portable? Would it fit in a car? Or is it only the size that might power a city? There are places that don't have access to energy, either oil or even sunlight, for example, and so, or tidal or hydro. So this would be transformative to civilization.
However, achieving nuclear fusion on Earth has proven to be a challenging task. The extreme temperatures and pressures required to initiate and sustain a fusion reaction are difficult to achieve and maintain. As a result, nuclear fusion is not currently a practical source of energy, but research into fusion technology continues in hopes of one day harnessing this powerful source of energy. Nuclear fusion reactions occur when atomic nuclei come together at extremely high temperatures and pressures, forming a heavier nucleus and releasing a large amount of energy in the process. This is the same process that powers the sun and other stars. The fusion of hydrogen atoms is the most commonly studied reaction, as hydrogen is the most abundant element in the universe. When hydrogen nuclei fuse, they form a helium nucleus and release a large amount of energy in the form of light and heat. This energy can be harnessed to produce electricity. One of the main challenges of achieving nuclear fusion on Earth is creating and maintaining the extreme conditions required for the fusion reaction to occur. The temperature required for fusion to take place is on the order of millions of degrees Celsius, which is much hotter than the core of the Sun. This high temperature is needed to overcome the electrical repulsion between the positively charged nuclei, allowing them to come close enough together to fuse. To achieve these high temperatures, fusion reactions must be carried out in a device called a tokamak, which uses powerful magnetic fields to contain the hot plasma, the state of matter in which the nuclei are able to fuse. However, even with the use of a tokamak, achieving and maintaining the conditions necessary for fusion is a difficult and complex task. Despite the challenges, many scientists and researchers believe that nuclear fusion has the potential to provide a nearly limitless source of clean and safe energy. Unlike nuclear fission, which is currently used to generate electricity, fusion reactions produce more energy than they consume and do not produce dangerous radioactive waste. Additionally, the fuel for fusion reactions, primarily hydrogen, is abundant on Earth. Research into fusion technology continues around the world, with the goal of one day achieving practical and sustained nuclear fusion on Earth. The first scientific experiments on fusion were conducted in the 1930s and 1940s, but it was not until the 1950s and 1960s that fusion research began in earnest. In the decades since, significant progress has been made in understanding the fundamental science of fusion and developing the technology needed to achieve and control fusion reactions. One of the main challenges of achieving fusion on Earth is creating and maintaining the extremely high temperatures and pressures required for the fusion reaction to occur. The temperature required for fusion is on the order of millions of degrees Celsius, much hotter than the core of the Sun. To achieve these temperatures, fusion reactions must be carried out in a device called a tokamak, which uses powerful magnetic fields to contain the hot plasma, the state of matter in which the nuclei are able to fuse. Despite the challenges, many scientists and researchers believe that fusion has the potential to provide a nearly limitless source of clean and safe energy. Unlike nuclear fission, which is currently used to generate electricity, fusion reactions do not produce dangerous radioactive waste. Additionally, the fuel for fusion reactions, primarily hydrogen, is abundant on Earth. Research into fusion technology continues around the world, with the goal of one day achieving practical and sustained nuclear fusion on Earth. Successful nuclear fusion has the potential to provide a clean and nearly limitless source of energy. In a fusion reaction, atomic nuclei combine to form a heavier nucleus, releasing a large amount of energy in the process. This is the same process that powers the Sun and other stars. Unlike nuclear fission, which is currently used to generate electricity, fusion reactions do not produce dangerous radioactive waste. Additionally, the fuel for fusion reactions, primarily hydrogen, is abundant on Earth. This means that fusion has the potential to provide a clean and sustainable source of energy without the environmental and safety concerns associated with nuclear fission. Another potential benefit of fusion is that it produces more energy than it consumes. In a fusion reaction, the combined mass of the resulting nucleus is less than the sum of the individual nuclei, and the difference in mass is converted into energy according to Einstein's famous equation, E equals mc2. This means that a fusion reaction can produce a large amount of energy from a relatively small amount of fuel. However, achieving practical and sustained nuclear fusion on Earth has proven to be a challenging task. The extreme temperatures and pressures required to initiate and sustain a fusion reaction are difficult to achieve and maintain. As a result, fusion is not currently a practical source of energy, but research into fusion technology continues in hopes of one day harnessing this powerful source of energy.